Thanks, Said. I'm going to talk today about some integrated photonics projects at Toptica. Now, of course, Toptica is a laser company, so we're looking at putting lasers onto integrated photonics platforms. So let me dive in here. I guess the first thing I want to talk about is why should we use PIC lasers? Um, and there's maybe two main advantages. One is that PIC lasers may give us the opportunity to provide lasers with specifications that you cannot otherwise get with existing technologies. First of all, of course, they offer a smaller package, but small lasers are available on other platforms as well, like DFBs and DBRs. But the other advantage that goes along with that smaller package on PICs is this opportunity to have a narrower line width. These advantages are going to be useful, particularly in applications that require both low swap and really high performance. So that could be field deployed clocks, gravimeters, Rydberg sensing, and so on. Um, on the other hand, another big advantage of PICs is, of course, all of the components that everyone around the world are developing to put onto PICs. So this is what I call the integration advantage. Having your laser, light manipulation, frequency shifting, splitting, and so on, and maybe even physics packages all on the same chip. That gives a high degree of integration, and this could have an advantage perhaps in lower cost, perhaps in lower power requirements. For example, particularly for the laser, if you need to get the light off of some chip or and then onto a chip, and then maybe onto a modulator, then back out, and so on. You have all these coupling losses in between. So having everything integrated could mean that you have fewer lasers or lower power uh, laser power altogether. And of course, this is useful for kind of everything. You could have even smaller quantum sensors as you scale up quantum computers and so on, and you need many wavelengths and many lasers to address many qubits. Having a high degree of integration could be a big advantage. More specifically on the spec advantage, I mean, Toptica offers a large range of lasers to get wavelengths in the visible and near infrared, all based on sort of making a tunable narrow linewidth laser around a laser diode. For a long time, we've offered external cavity diode lasers that rely on bulk optics to provide external feedback that allows you to get a tunable laser. These are our DL Pro and CTL platforms that give you wide tuning, narrow line width, and so on, so you can address any atomic transition. But these are big, bulky lasers. They cost, a fair bit of money. Um, and yeah, and particularly if we're talking about low swap applications, they're not going to be suitable outside of a laboratory. DFB and DVR lasers exist, but there are many gaps in wavelengths that they cover. It's pretty difficult to design these lasers to reliably reach the target wavelength every time you fabricate them. And so this investment to fabricate these lasers has really only gone into wavelengths where there's really a key application where that will be profitable. So this is 633 nanometers where Heine lasers exist, 780 because rubidium's a pretty widespread atom that is used. But you can't really get DFBs and DVRs at all wavelengths that might be useful, particularly for quantum computers or some sensors. And their line width can be pretty big, hundreds of kilohertz to a megahertz. Um, in the last few years, Toptica's subsidiary Eagle Yard developed the Mini ECL, which is an external cavity laser like the DL Pro, but it's all developed or packaged via micro optics. So you have very small feedback elements that feedback light to the laser diode. And these are very nice devices. They're already very small. They get pretty good line width. We can, in principle, develop them wherever there is a laser diode. So sort of the maybe 370 to 2 microns. Um, they have a limited mode hop free tuning range. Like I said, the limit is pretty good, but maybe not suitable for extreme clock applications. And now we're investigating this new technology where people are using photonic integrated circuits to provide feedback to a laser diode. We've been looking at this for a couple of years now as well. Internally at Toptica, we have some funded programs where we're developing these lasers. And there's a potential to have a superior technology to the Mini ECL because we can get potentially wider mode hop free tuning and potentially much narrower line width. So these are sort of the spec advantages that a PIC laser can provide if you just want to have a standalone laser. Um, but I think I think that there are only a limited number of applications where that's going to provide a really big advantage. The big advantage is an integration. You can have this standalone product, but you could consider within a single package, sort of co-packaging or edge coupling multiple different PICs, gain material, sort of hybrid integration of many different components. But increasing integration is having a foundry that has some PDK where you can drop in a laser and modulators and physics packages and so on, ion traps maybe all onto the same chip. And I think that that's the real promise that we're all working towards. But so far, for the most part, people are demonstrating each of their individual components. And I think it remains to be seen whether that's going to be the real solution. The biggest problem in my mind with that is that if something breaks, then you throw out the whole thing. But we'll see. We'll see how that all comes together. But Toptica's efforts on integrated lasers, so far we've investigated two approaches. One is called a self-injection locked laser, and the other I'm calling a two-ring Vernier external cavity laser. In a self-injection locked laser, we use a Fabry-Perot laser diode, which means that this diode would laze on its own because it has reflections at the interface at both interfaces, and then we provide this PIC, which basically provides feedback that self-injection locks the laser. Whereas in the two-ring Vernier external cavity laser, we use an AR-coded semiconductor optical amplifier and then provide feedback from the structure that you see here. The Vernier device we've investigated at 637 nanometers as part of a funded project. This is published at the link here. We have different configurations here, but in one configuration we saw very large mode hop free tuning, pretty good intrinsic line width on the order of hundreds of kilohertz, and on the order of 1 milliwatt power. We were able to get that with narrower line width below 10 kilohertz, a little higher power with a little sacrifice in mode hop free tuning range. In both cases, we could tune pretty much over the entire gain bandwidth of the diode with coarse tuning. And then in a few weeks at the laser, or actually in our Quantum World of Photonics booth in Munich, we'll be showing our demonstrator of a 780 laser. This has intrinsic line width below a kilohertz, so this can get to 778 nanometers, for example, for 2-photon rubidium clocks. It has pretty good mode hop free tuning. In free space, we have 30 milliwatts. In fiber, at least 10 milliwatts. You can see some performance specs here. So yeah, this will be at our booth in a couple weeks. Yeah, and that's basically what I have. Like everyone else, eager to hear about collaborations. This operating device we have at 780 nanometers. We're happy to bring it to people's labs and see if they see an advantage of having a relatively small laser with pretty narrow line width. Something that I should note here is that maybe many people have seen Toptica laser heads that all look to be about this big. So what's the point here? The main point here is that this laser head contains the packaged laser as well as all electronics. So this thing just plugs into the wall, and it's about the size of a small shoe. So we're pretty excited about that for low swap applications. So yeah, let us know.